This video is part of the lecture for multivariable calculus, and I'm going to talk about double integrals over rectangles, basically iterated integrals. So let me start. If we have a double integral of a function of two variable f of x and y dA over the region R, where the region R is from AB on x-axis and CD on the y-axis, basically when we have a rectangle in here, we can use the Riemann sums to solve them, which we covered in the previous videos, and we can use the iterated integrals. This method, I'm gonna talk about it right now. So geometrically, what are we gonna do? Geometrically, I really want to have a good graph in here because it's very important. So this is x-axis, I have y-axis, and I have z-axis in here. Then I have a function like this. Just assume that I have this function in here, and the function is f of x and y. Then I have a region on xy plane. So let me try to have basically a good region in here, which is this rectangle. So x is from A to B, and then y is from C to D, and basically this is my f. This is part of the f that is above the region R, like this. Okay, and I have the region R down here. Now I would like to say that the double integral we covered before. The double integral is basically the volume of a solid that is bounded above by the function f, the integrand, and on the bottom is bounded by the region R. Okay, so I would like to find the volume of this solid in here. So using the iterated integrals, what I'm gonna do, I'm gonna take slices. But how I'm gonna do that? I'm gonna have another graph. I know it's gonna take long, but it's really, I think, important that we visually understand what's going on. Y-axis, and we have z-axis. Again, let me graph the function. It's like this. This function is actually, it's bounded above it's above the region R. It's part of the function that is above the region R. Region R is basically here. Okay. Let me make it a little better so that we actually see what's going on. Okay. We had what this is AB, this is C and D. So let me basically move y in here. We have some space. There you go. CD. Okay, now I'm gonna take slices. How? I'm gonna do it like this. I'm gonna kind of slice this um, solid that I have in here by a plane that is perpendicular to the x-axis. I mean, like, just assume that this plane, okay? Okay. So I cut this solid. I take one slice of this solid by cutting it with a plane that is perpendicular to the x-axis, and I'm gonna call just the area in here that I kind of get as the intersection of the plane with the solid. I'm gonna call it A of X. Okay, so I'm gonna say let A of X be the area of this slice that we get it by the plane perpendicular to the x-axis. So the plane that is perpendicular to the x-axis, I mean, it's parallel. This slice is parallel to z plane. Okay, which means what? Which means that x is held constant, right? So as you see on this slice, on this plane, x is constant, somewhere between a and b, x is constant, and y is between c and d. Y is changing, you see, y is between c and d, but x is fixed. X is just some constant. So in that case, I can basically calculate a of x. So what is a of x? A of x is the area in here that is below just this curve, and I got this curve in here by just taking this slice. Okay, so what is this curve in here? This curve is actually f of x and y, where x is fixed, right? X is actually exactly this value that by fixing, by slicing the graph. So x is fixed, and so I get exactly like what we did on the one variable calculus. F of x, x is fixed, and then y is the one that is changing. So a of x is just the integral of this curve, and this curve is f of just some scalar, some value when x is fixed, and then y is changing dy from cd. So this one we already know how to calculate. Now when I want on the second step, this was the first step, on the second step I'm gonna find the volume, and I'm gonna say that the volume is what? Is basically I just need to add up all these slices, right, to get the volume. Just assume that we have like a solid in here, and then we just make it like slices, and then we just need to add up all the slices to get the volume that we want, right? So the volume would be the integral from a to b of ax dx, right? And let me just replace ax but what we have in here. So I'm gonna write ab, and then for ax it would be cd f of x and y dy. That was a of x, and then dx. So basically this is the area under the function f, where x is fixed and the dx in here is just basically the thickness of the slice, right? So we just have a little bit of thickness in here, and then we just add them all up, and you see that we calculate the volume, which is perfect. So we just take the integral from AB, and then we take the integral from, actually we start from the inner integral. We take the integral from C to D of the function f dy, and then after we calculate that we get dx. So basically let's see how to calculate it. For that was the geometric meaning of the iterated integral, that as you see we take slices. We have a solid, we take a slice, and then we have the area, and then we have some thickness between all the slices, and then we just add them up, considering the thickness times the area, and then we just add them up. That's what we get. So now for the computation, so computing, how to compute the iterated integral. The first one is that the inner integral for the inner integral, okay, for this one. For the inner integral, x is fixed. We integrate with respect to y. Basically just assume that x is just some constant. Okay, that's it. And then after that the result can depend on x, right? But no longer involves y. Why is that? Because if you take the integral in here with respect to y, then y is from C and D, so we're gonna replace all the y's that we have with C and D using the fundamental theorem of calculus. So that's all we get is just x. We just have x, no y anymore. And then on the third step, we're gonna say that then the outer integral, for that we just integrate with respect to x, right? And then after that, when we take the integral, the outer integral with respect to x, using again the fundamental theorem of calculus, we are going to replace x, all the x's by b, minus replace all the x's by a. So we don't have any x, we don't have any y, nothing else. So at the end of the day, the result is just a number for these specific integrals, right? So let me just do one example of how to calculating that. So I'm gonna do an example. I'm gonna calculate the integral of x squared y dA over the region R, which is 1, 4 times 0 and 2. Okay, let me make it just a little small so that we see all the steps. Okay, so first I want to write the bounds. I'm gonna write the double integral, I have my function which is x squared y, and then for dA I'm gonna write the inner integral as dy. So when I have dy in here, I need to pay attention to y's. So y's is from 0 to 2. That's why I'm gonna put the bounds for y in here, right? Okay, and then for the outer integral, because I have dx for the outer integral, I need to write the bounds for x, which is basically the first interval for the bounds of the outer integral, 1 to 4. So pay attention to all these details. Okay, so I'm gonna calculate the inner integral. So I'm gonna write the outer integral. I'm not gonna change it. And then I'm gonna just calculate the inner integral, this one. Okay, how do I do that? X is fixed, okay? X is just like a constant, and y is my variable. So like assume that you have 5 squared times y dy. So what is the integral of that? It would be x squared, the constant, and then derivative, antiderivative of y is y squared over 2. And then don't forget that you have some bounds, so it would be y from 0 to y equals to 2. I always recommend to my students that for the double integral or even triple integral, always write the variables for your bounds. It would be very helpful, because sometimes if you don't write, you forget, and then you plug in, for example, the bounds for y for x, it would make everything wrong. So do that. And then what do I get? I get the integral from 1 to 4. For y, I'm going to plug in 2. So I get x squared. And then I get 4 over 2 minus, I'm going to plug in 0. I get x squared 0 over 2. So this is just 2x squared. This is 0. And then don't forget that we have a dx in here. So now I have the integral from 1 to 4 of 2 x squared dx. You see, we calculate the inner integral. The result can depend only on x, just because I put the bounds for y in here, so I don't have any y in here, so I only have x. Okay, this is my outer integral. This is my outer integral, which is basically just a simple integral. What is the integral here? It would be 2x cubed over 3. X is from 1 to 4. Plug in 4, I get 2 4 cubed over 3 minus plug in 1 cubed over 3. Do the calculation, the answer is 42. Okay, that's how we compute a double integral. Let me give you just one small note. Do we always need to write dy first and calculate that? If we want to talk geometrically, instead of taking the slices as perpendicular to the x-axis, you can take the slices perpendicular to the y-axis, right? And then your thickness would be like dy, right? So there is not much difference between taking the slices in x-axis or y-axis. So I can say we can also integrate in the other order. How? I'm gonna say that the integral of f dA over the rectangle R is, just assume that your rectangle R is AB cross CD. Okay. Now I can write CD and then AB f of x and y. Okay. And I write dx in here, which means what? Which means that on here you can regard y as a constant. So slice with y equals to some constant c, right? With a plane perpendicular to y-axis in this time, right? And then, so this is the area of your slice. If we have the shape like that, let me just quickly, very small, I'm gonna say this is z-axis, this is y-axis, and then if this is your f, your function f, we're gonna slice it with a plane like this. Then you have a of y, you see? And then this is the area of your slice, and then we have dy as our thickness, and that's how you can calculate that. So is this always true? Can we exchange the order always? This is the subject of Fubini's theorem. So Fubini's theorem says what? Says that if f is continuous over the region R, which is AB cross CD, then the double integral of f of x and y dA over R, you can write this as f, you can write dx dy, okay, which means that the x is first. When x is first, I need to write the bounds for x inside. Pay attention to all these details. And then dy cd, or you can write f dy dx. In that case, you have cd in here, and then dx a b in here. Okay, so we can exchange the order when f is continuous, but should always this is true for always for when your function is continuous, or do we have any other cases? Like more generally, I can say more generally, if your function is not continuous, but you have these conditions. If we assume that if your function f is bounded on the region R and f is discontinuous, only on a finite number of smooth curves. So we have discontinuity only just on a finite number of smooth curves, and the iterated integrals exist. So your function is continuous on the region R. It has only a finite number of discontinuities, and the iterated integrals, I mean these ones, they exist. Then we can exchange the order of integration when we have rectangles. Okay, this is the subject of Fubini's theorem. On the next video, we're gonna solve some examples.